Hello and welcome to the YouTube channel of AI with Vic, and today we will talk about determinants in details. So we will go through the process of understanding first cofactors and minors. Then I will try and give a formal definition of determinants. Then we will try and give a definition of determinants to calculate the determinant. Uh, then we will try and understand singularity, adjoint, inverse of a matrix, and the final is the row reduced echelon form. Uh, this is one of the most important concepts in linear algebra, and we will show that why this is important and how in today's world it's being applied to one of the major research areas. Okay, so let's start with understanding cofactors and minors first. So what is a cofactor? So let's say, for example, that if A, let's first understand a minor. So let's say, for example, that let A be a determinant of order n. Let's say, for example, A is of order n, right? Then the minor of Aij, like let's say, for example, if this is the matrix or A12, A13, A21, sorry, A22, A23, A31, A32, A33. If we consider its determinant, it's A11, A12, A13, A21, A22, A23, A31, A32, A33. Then the minor is basically a subdeterminant of order n minus 1, which is obtained by basically leaving the ith row and the jth column of determinant A. So let's say, for example, what do I mean by this? Like, this is a formal definition, but let's say, for example, if I am considering the minor of A11 here, A11, then it will be calculated as by removing this row and this column and obtaining A22, A23, A32, A33, right? So this is the minor of A11. Similarly, we can calculate the minor of A12, which will be basically removing this and this, right? This column and this row, and this will be the minor of A12, like this element, this element, this element, and this element. Now let's understand the cofactor. What is a cofactor? By definition or by formulation, a cofactor is defined as minus 1 I plus j into m I j. So what do I mean by that? A cofactor of, let's say, for example, A of A11, right? What will be the cofactor of A11? Let's see here. It will be cofactor of A11 would be minus 1 to the power of I plus j. This is I and this is j. 1 plus 1, and then basically minor of A11, which is A22, A23, A32, A33. Ultimately, this calculation would be minus 1, this is basically positive, A22, A33 minus A32, A23, and this will again be a scalar quantity or whatever magnitude that we get here. So this is the definition of cofactor and cominor. Now let's get into the formal definition of a determinant. What is a determinant? So basically, a determinant can be defined as a scalar quantity. Basically, let's say, for example, that if you have a matrix of order n, basically meaning a square matrix of order n, then its determinant is a scalar quantity, right, which is associated with this matrix A. And how is it calculated? Let's give a formal definition of the of the calculation of determinant A. Now remember, this is the matrix that we are considering, like A, right? Now if we want to calculate the determinant of matrix A, then it should be something like this. Let me just clear this up. Eraser, just clear this up. We have this matrix A here, and if we want to calculate the determinant of A, then this is going to be cleared up here. Yeah, so this is the value. Delta is equal to J is equal to 1 to N, and then Aij, right? Now don't be just don't be afraid of this complete definition. Let's try and understand. The determinant of A can be calculated along the row also or along the column also. This is the first thing. So when I say J, that means I'm trying to calculate the value of determinant along the column. This can be also be written as along the row, I is equal to 1 to N, Aij. So let's try and expand this for this particular matrix A, or the determinant value of A. So this will be equal to, along this row, let's say for example we are trying to calculate along the first row, and it's not necessary that you calculate for each of the rows, just first row or any column you can choose, right? So let's say for example this will be the value A11 dot cofactor of A11, right? So the cofactor of A11 would be -1 to the power of square, right? And let me just get my rubber here, right? Yeah, A11 -1 square, and this would be A22, A23, A32, A33, okay, and then plus, again we are considering A12 here now, so it will be A12 -1 to the power of 1 plus 2, 3. That will be A21, A23, A31, A33, right? And then plus again A13 dot let me just go down here, dot -1 to the power of 1 plus 3, which is 4, right? And that would be A21, A22, A31, A32. So this is like I have expanded along the first row here, and you can see that this way we can calculate the value of a determinant associated to a matrix, right? So now an important concept that we would like to go forward with is understanding singularity. So what is singularity? Singularity of a determinant basically says that the determinant value of should be, let's say for example, if you have a square matrix A of order n, basically order n by n, then it is said to be singular if determinant of A is equal to 0, or basically the value associated with the matrix, the determinant that you are trying to calculate, is 0. By the way, we have come this far in the determinant. Have you thought what is determinant actually? Like, determinant gives a value. So what it is? Is it a vector or a scalar quantity? The answer is that it is a scalar quantity. Great. Okay. Now we will try and understand few properties of the determinant also before we move to the part of adjoint and inverse of a matrix. Now let's try and understand few properties of determinants. I will try and show the examples for almost all properties. So let's first try and understand the first property, that is determinant of identity matrix, which is basically always 1. So let's take for example A is equal to 1 0 0 1, which is an identity matrix, which implies determinant of A would be 1 minus 0, which is basically 1. It's an example. So this basically holds for identity matrix of order n. Like if you consider like a matrix of order 3 1 0 0 1 0 0 0 1, like it's the same result, like the determinant is always 1, right? The next important property that we can observe is that interchanging two rows or columns changes basically the sign of the determinant. So let's take for example one example for that. So we have a matrix, let's say for example A is equal to 1 2 2 1, right? And its determinant would be 1 minus 4, which is equal to minus 3. Now if we interchange the rows, so basically let's say for example A prime is equal to, we basically take 2 1 1 2, and then its determinant, which is basically 4 minus 1 is equal to 3. We can see that basically the sign has changed here, right? Now one of the most important properties for calculation of determinant is identical rows or columns. What does it mean? Is basically, let's say for example if we have a matrix A, right, and if we take it as 1 2 3 1 2 3 3 4 5, then the determinant of this matrix will be always be 0. So let's try and calculate that. So determinant of A would be 1, then 2 3 4 5 minus 2, and it will be 1 3 3 5, and then again plus 3 will be 1 2 3 4, right? If we go below, it would be 1 10 minus 12 minus 2 5 minus 9 plus 3 4 minus 6, right? So minus 2, which is minus 2 minus 4 plus 3 minus 2, which will be equal to minus 2 plus 8 minus 6, which is equal to 0, right? Great. The other, I will try and solve for almost all properties. The rest I will request you guys to try it with your own like copy and pen. That's the best approach. Let's try and solve one and couple of more. So let's say the fourth property says that 0 row or column. So basically it says that the fourth property, that if you have any matrix A which has got a 0 row, then its determinant is 0 1 1 2 1 2 4. And you can observe this, like if we try and calculate a determinant of A for obvious reasons, like if you, this will be 0 and 1 2 2 4 minus 0 again, it will be 1 2 1 4, and again plus 0, it would be 1 1 1 2. Now obviously all the elements are here multiplied by 0, so it will be 0. So right, great. Another important property is the fifth property. If we try and look at it, is the scalar multiplication of a row or a column. So basically it says that if one row is multiplied by k, then determinant of A prime is equal to k of determinant of A. One row, not all. Like, so let's try and solve this, right? So if you have matrix A is equal to 1 0 1 0 1 0 0 0 1, and if we consider let's say for example k is equal to 2, then a prime, I am trying to multiply it by the first row here, becomes 2 0 2, 0 1 0 and 0 0 1. So then in that case determinant of a prime would be 0 0 2 1 0 minus 0 2 0 0 0. I'm calculating around from this row, right? Remember, we can calculate from any rows and any columns in determinant. Plus 1 and then 2 0 0 1, which is equal to 2, right? Now if we calculate the determinant a in its original form, let me just clear this up a bit. Right, so we are back here. If we calculate the determinant of a in its original form, we have 1 0 1 0 1 0 0 0 1, which will be equal to 1, right? If you just basically try and calculate around this row, so which basically shows that k of determinant a is equal to determinant of a prime, which actually proves the property 5. Similarly for property 6 is the same thing, like if all rows are multiplied by scalar k, like basically it says that the whole matrix are multiplied by the scalar k, then it becomes determinant ka is equal to kn of determinant a. If you want, we can try that out. Let's try it out, and the rest of the properties I would request you guys to try it on your own and let me know in the comments, like if it works or not works, or if you are facing any kind of difficulties. I will try and solve that. So let's try and see property 6. Okay, so according to property 6, we have determinant ka is equal to k to the power of n determinant of a. Basically it says that if there is a matrix, let's say for example a is equal to 1 0 1 0 1 0 1 0 0, which is of order 3. So let's take k is equal to 2 here, then determinant of ka will be equal to basically 2 0 2 0 2 0 2 0 0. Now if we calculate the determinant of this, it would be calculating along this particular row, it will be minus 8. And again, if we try and calculate the determinant a, we'll try and again calculate along this particular row here, it would be minus 1. Therefore determinant of ka is equal to minus 8, and determinant, let's say for example here it says k to the power of n means order of a matrix here. So k is 2 to the power of 3 into determinant of a, which is equal to minus 8, which is same. So property 6 also holds good. I would again request you guys to go through all the properties here, rest of the properties here, and let me know in the comments again, like which works, which does not work, and we can try and solve those properties. Now we will move to the part of adjoint calculation. Let's understand the adjoint calculation by giving a formal definition. So let's say we have a matrix here, A is equal to Aij, right? Then the formal definition basically says that adjoint of A is equal to Cij transpose. Now let's break it down. What does Cij represent? Cij is basically the cofactor of an element Aij. So it should be minus 1 I plus j Mij. Again, what is Mij? Mij is the minor. So if, for example, we have a matrix as A is equal to A11, A12, A13, A22, A23, this is A22, A23, A31, A32, A33, then adjoint of A is defined as C11, C12, C13, and then again C21, C22, and C23, C31, C32, C33. Right? And then we take a transpose on top of it. Right? Now let's solve an example for it based on the definition. So let's say, for example, we have a matrix. Let me just clear this out. Now that we have the formal definition, we can just try and solve an example based on it. This is goes here. So let us say that we have a matrix A is equal to 1, 2, 3, and then 0, 4, 5, and 1, 0, 6. Right? So what will be the adjoint of it? Basically, adjoint, by the definition, it says that for each of the element we need to calculate the cofactor, right? For like 1, 2, 3, 4, 0, 4, 5, 1, 0, 6, for each element we need to calculate the cofactor first. So let's do that. We will draw a table for that for better understanding. This is first like the step 1, right? This is the element. Then we have the minor, like the Mij for each element, and then finally we have the cofactor. Let's start. So for, let's say, for example, we first list down the element that we have 1, 2, 3, 0, 4, 5, and going down we have 1, 0, 6. Okay, let's start by 1. The minor would be like we eliminate this row and this column. So we have 4, 5, 0, 6, which is equal to 24. What will be the cofactor here? It's I plus j, right? Minus 1 to the power of 1 plus 1, right, into 24, which is 24. Right? I just showed it the whole thing for the first element, and I will just simplify for the rest of them. Okay, so for 2 it will be again 0, 5, 1, 6, which is equal to minus 5. What will be the cofactor? Minus 1 minus 5 is equal to 5. For 3 it will be again 0, 4, 1, 0, which is equal to minus 4, which is equal to again just plus 1 minus 4, which is minus 4. 0, if you consider, it is 2, 3, 0, 6, which is equal to 12, which is minus 1, 12 is equal to minus 12. Right? And then we have for 4, we have 1316, which is equal to 3, and then again C22, which is plus 1 minus 1, sorry, this will be always minus 1 to the power something, to the power of 3, which is again this is C33, right? 4, this is again 3. Now for 5, similarly for 5 here, it will be 1316. This is 13, so this is 1316 here. Already we have calculated here. So for the rest of the element, I will just write it down what they are. For 106, it is minus 2. This is for 5, this will be 5, this will be 4, and here again it will simplify. This will be minus 2, this will be just minus 5, and this will be 4, right? So you have all the cofactors here for each of the elements, right? So below, then the cofactor matrix that you get is as follows. Which is C equal to 24, 5 minus 4 minus 12, 3, 2 minus 2 minus 5, 4. So adjoint of A will be now equal to C transpose. Basically this is the cofactor matrix that we have already got. So if we do a transpose, it will be 24 minus 12 minus 2, 5, 3 minus 5, and minus 4 to 4, right? So this is the adjoint of A that we have just calculated. Remember always that the formula is very simple and it's easy to implement if you do it in a tabular form like this. If you have any problems in understanding the calculation or any part of the context of adjoint, please comment and I will explain it again. Okay, so let's try and understand now for the same thing, like if we want to calculate the inverse. So you have the inverse right here. We already have an adjoint here. So let's extend it by understanding the inverse of a matrix. What is inverse? Inverse of a matrix, like say for example A is equal to Aij, is denoted by A inverse, right? And its formula is A inverse is equal to 1 by determinant of A multiplied by adjoint of A. Evidently, this also says one thing, that if determinant of A is equal to 0, or if A is a singular matrix, remember the concept that we have already shown. If A is a singular matrix, then the inverse of A is not possible, right? Now from the above matrix, if we want to calculate the A inverse, what it will be? Like A inverse will be like, let's first calculate the determinant of A. This is here. The determinant of A, I am calculating it along this particular row that you have here, right? 1 into 2, 3, 4, 5 minus 0 and 1, 3, 0, 5 and plus 6, 1, 2, 0, 4, which is equal to final, if you break it down, this is 10 minus 12 minus 0. Obviously this whole thing will become 0 whatever you do. 5 minus 0 plus 6 into 4 minus 0. Now if you see here, it will be 20, right? Now let's move to the inverse calculation. A inverse then will be equal to 1 by 20 into the adjoint of A that we have already calculated from above, which is 24 minus 12 minus 2, 5, 3 minus 5, and then minus 4 to 4. That will be equal to 24 by 20 minus 12 by 20 minus 2 by 20, 5 by 20, 3 by 20 minus 5 by 20 minus 4 by 20, 2 by 20, and 4 by 20. Right, if we try and simplify this, this will become, this is 4, 6 are 24, 4, 6 by 5, which will be 4 minus 3 by 5, this will become minus 1 by 10, this will become 1 by 4, this will become, again this will remain same, this is 1 minus 1 by 4, this is minus 1 by 5, this is 1 by 10, and this is 1 by 5. Right, so this is A inverse for you. Okay, now we will move to understanding the row reduced echelon form. So the row reduced echelon form is one of the most important concepts to understanding the next part that we will be doing, the Gauss elimination method, and we will be also solving code examples based on that. So let's move to it. Okay, so to understand the row reduced echelon form, we will first try and give a formal definition as we have been giving for each of the concepts and previously also. So a matrix A is equal to Aij is row reduced echelon form, or RREF, if it satisfies 4 points. Let's understand those 4 points in details. Point number 1, leading pivots. What do we mean by that? That it means that each first non-zero element is non-zero row is 1. So basically the first non-zero element in a particular row, let's say this is a matrix and this is A11, A12 and so on. So if we consider this particular row, then this should be 1. Right, this is the first non-zero row, then it should be always 1. Right, the leading pivot is always 1. The second point, zeros below pivot. Zeros below pivot. Continuing with the same example, if this is a pivot, then below this and above this, if there are any rows, then it should be all zeros. So this will be all zeros here. Right. The third most important point is the row ordering. Right. Any row that is 0 appears below all non-zero rows. So basically it means that any row that is 0, so this is 0 basically, let's say for example, if this is a 0 row, right, so it should appear above all non-zero rows. So meaning, so let's say for example, let's understand in a bit detail row ordering. So if this is a 0 row here, right, then this should be the last row, basically saying above all it should be all, there should be the non-zero rows. Right, this is non-zero row, this is a non-zero row, this is a non-zero. Below this, no row should be basically on a non-zero row. If there is, you can always order it again. And the fourth point is pivot position to right. Pivot position to right. Basically it means that pivot of each successive non-zero row is right of pivot. So basically it means that if this is a non-zero row that you have here, let's say for example this is a non-zero row, A11, A12 and so on, this is A21, A22 and so on. If this is 1, this is the leading pivot here, then the second pivot should be always here, obviously, because below this all are zeros, right? So it should be always on the right. right? Okay, so using these 4 points, right, we will try and reduce a matrix to its row reduced echelon form. Let's take an example for that. Let us take A is equal to 1, 2, minus 1, minus 4, 2, 3, minus 1, minus 11, minus 2, 0, minus 3, 22, right? So let's start with step 1. So leading element is already 1, so we need not do anything here. So step 1 is done. Let's move to step 2 here. The step 2, we need to reduce this below 1, right? That's the first step. That we need to reduce these rows, or below 1 it should, these elements should be 0, right? Remember, zeros below pivot, right? So let's do that. So how can we do that? We can perform row operations on it. R2 is equal to, we will do the transformation of R2 minus 2R1. Just a minute here. Eraser. Right. And also we will perform R3 operation, an operation on R3. On R3, we perform the operation of R3 plus 2R1, which actually gives the matrix transformation as 1, 2, minus 1, minus 4, 0, minus 1, and this will be 1, minus 3, 0, 4, minus 5, minus 14, right? So we now have the first step, like you can see here below the pivot there are only 0 elements. Now for step 3, we will again reduce this part to a pivot of first leading element. So that can be done by R2 is equal to minus 1 into R2. So basically the idea is that you need to go forth and back on all the 4 points that you have. There's no correct order of where you want to go, but you need to go from 1 to 2, then again back to 1, 1 to 3, then again 3 to 1, like that, whichever suits you, to bring that the matrix to a row echelon form. So we have here from R2 transformation 1, 2, minus 1, minus 4, 0, 1, minus 1, 3, and 0, 4, minus 5, 14, right? For step 4, we will again do a transformation of R1 is equal to R1 minus 2 R2, and R3 is equal to R3 minus 4 R2, which actually will give this matrix transformation to here. R1 is equal to 1, 0, 1, minus 10, and then 0, 1, minus 1, 3, 0, 0, minus 1, 2. So why did we do this transformation? You can now observe that in the second step we have 0 below pivot, right? So this we recognize that this is the leading element for row 2. Then below this and above this there should be the 0 elements. So for this we perform this transformation. You can see here below and above there are 0 elements, right? Now for the last transformation that we will have here, not the last, second last probably, I guess. So let's try that. S5 again, R3 is equal to minus 1 into R2, which will actually give 1, 0, 1, minus 10, 0, 1, minus 1, 3, and 0, 0, 1, minus 2. Let me remove this. Right, we back here. Now you can see this matrix. This is the leading, this is a non-zero row and the leading element is 1. Below this is zeros. This is again the leading element 1. Above and below are zeros. For the third row, you can still observe 1 and minus 1. So we will do a last transformation to reduce that. Let's do it. The step 6 will be R1 is equal to R1 minus R3, R2 is equal to R2 plus R3, which implies the reduction to 1 0 0 minus 8 0 1 0 1 0 0 1 minus 2, right? So we have here the row reduced echelon form, right? You can observe that for each non-zero row the leading element is 1 and below this there are zeros. To the right there is the second pivot, which is for the row 2. Above and below are zeros. For again after for the third row to the right we have the last pivot element 1, a non-zero row, and above which there are 0 elements. Now what does it basically imply? This basically calculates the rank of a matrix. Rank of a matrix. Now the important point about rank of a matrix is that row rank is equal to column rank of a matrix, right? So basically it says that the number of non-zero rows in the row reduced echelon form gives you the rank of a matrix. So here how many non-zero rows that we have? 1 2 3. So the rank of a matrix is 3 here, right? Now we will talk about an important concept of linear independence. Okay, let's try and understand one important concept, that is linear independence. It's a very important concept in linear algebra, and going forward, whether you research in the area of computer science or math, this is going to be a pivotal, right? So let's say, for example, if we have a set of vectors of v1 v2 up to vn, then this set of vectors v1 v2 up to vn is said to be linear independent if no vector in this set can be expressed as a linear combination of the others. So basically v2 cannot be written as like some constant of v1 or some plus some constant of c2 c2 v3 c3 v3 and or any other combination. Basically meaning that if we have an equation like this, c3 v3 plus dot 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 up to cn vn is equal to 0, then the only possible solution to this particular equation is that c1 is equal to c2 is equal to cn is equal to 0. Okay, let's understand this concept on the row reduced echelon form matrix that we have just done here. So you can see here that this is the row reduced echelon form. Let's consider this particular as v1 vector, this particular column, this as v2 vector, this as v3 vector, and the last as v4 vector, right? Now observe that v4 vector can be written as a combination of minus 8 into v1, right, of 1 into v2 plus sorry this is plus, my bad, plus v2 plus minus 2 into v3, right, where v1 v2 v3 are these vectors like 1 0 0 0 1 0 0 0 1, right? So basically which states that v4 is dependent on the vectors of v1 v2 v3. It can be expressed as a combination of v1 v2 and v3 here, right, which means that v4 is linearly dependent, right? And v1 v2 v3 v1 v2 v3 is linearly independent set of vectors, which also states that the column matrix, or sorry, the column rank of this matrix is basically 3. Like because you have got like 3 linearly independent vectors. Remember that we found out also that the row rank of this matrix is 3. So and we also showed that the row rank is equal to the column rank, so which basically also proves that fact here, right? Great. Now this concept has been applied to a very recent and powerful research called LoRa, low rank adaptation of large language models. This is an important milestone in the research of AI or large language models that we all know. This concept or this paper was released in 2021, if I'm not wrong, and we will talk about this like for 5 to 7 minutes to understand how this concept has been applied here. So, what is the motivation for LoRa? We need to first understand this. So, as you know that there are a lot of large language models or AI models that you might have heard about. I'm not trying to go deep there, but trying to give you an intuition of what it is and how does it work. So there are a lot of large language models that you might have heard about. Let's say, for example, ChatGPT. ChatGPT is a large language model. ChatGPT or Cloud, BERT, GPT-2. So these large language models that we have here uh, can be fine tuned. What do you mean by fine tuned? Basically, in a single sentence, if I want to make it understand, adapting to your own personal data. Let's say, for example, if you have a large language model and you want to fine tune it to your company's data, make it specifically answer according to your company's data, you can do that. That process is known as fine tuning. But basically, before LoRa, what happened was fine tuning required a lot of parameter updation. So let's say, for example, a large language model like ChatGPT um, could have like close to uh, 400 billion parameters. Basically, fine tuning this large language model meant like updating all the parameters that you have. But what LoRa said was, LoRa says that instead of updating all these parameters that you have, like all the 400 billion parameters, just approximate the weight updates using low rank matrices, right? So let's define it mathematically, right? You have, let's say, for example, a very large language model and whose pre-trained have weight like metrics like these weight metrics that you have, the 4 billion parameters like R, D, K. Like this is the dimension of the matrix. It could be very large. But what happens during traditional fine tuning? That you have W is equal to W plus delta W, right? Where delta W is a full rank matrix, basically very large, right? Uh, just a minute, just very large. But what Laura said was uh, that you have got put delta W is equal to uh, A B, right? Where A will be belonging to the dimension of R D cross R and B will be belonging to dimension of R cross K, and R, where R is going to be defined as minimum of D comma K, a very small number. You can say that it could be between 4, 8, 16, like but these numbers basically depend on different models, like models like GPT-2 or BERT could be between 4 or 8 or something like that, right? Uh, now, so basically, instead of learning these many parameters that you got, like all the d cross k parameters, LoRa basically states that you can just concentrate on this matrix, that is delta W, by decomposing into A cross B, and that reduces the parameter learning to just R D plus K. That's it. Let's take an example. Like, let's say for example you have got a very large weight matrix, right? Let's say for example of W is equal to 4096 cross 4096. Right? This is very large, right? And this means that it could have a parameters close to 16 lakhs or 1.6 crores, and I think 1 crore 67 lakhs something something. If you multiply this, you will get this parameters. Now, according to LoRa, this parameter, I mean, like if you go by traditional fine tuning, this you need to update, like all these parameters that you need to update, like so many parameters and so much of time. But LoRa says that this could be reduced to what? R. Let's say for example if we take R is equal to 8, then this could be reduced to R 4096 plus 4096, which gives you just 65,500 and I think 38 parameters most probably. So basically from here to here, right? So that's the motivation behind understanding uh, these matrices and determinants and rank in a matrix. Now, what does a low rank matrix means? A low rank lives in a lower dimensional space, like a much lower dim space that you have, rather than a full rank matrix, which is kind of a very high dimension. High dimension means requiring lot more memory and lot more time also to fine tune, right? Now, I've like basically tried and plot updation scheme for the LoRa or using a dummy matrix, right? And I will try to explain to you like what it is. So on your left side that you got, like if you see here, you got like W true, right? What does it mean? Like this is basically the ground truth that you can see here. Ground truth. What do you mean by ground truth? Like let's say for example, if I say looking at a picture of a cat that it is cat, but the machine says that no, it's a dog. So what I have said by looking at the picture is basically the ground truth, that yeah, the gold label, right? This is the ground truth of the matrix, right? And this is the target matrix that we want to approximate. Now if you see here, this is basically the low rank matrix reconstruction that I have tried out here. And if this basically if this works here, like as you can see, as LoRa is working here, this matrix and this matrix are very close to each other. And what is this matrix? This matrix is basically error. This is bland and this should be bland as much as possible, so that if it has got dots here, that means that we are not approximating well, and this will basically go bland. This color and this color will not match. Understand in a very simple way. I'm trying to make a point here that if this is the ground truth and this is the decomposed matrix that you are having from LoRa's algorithm, this and this matrix are very close to each other, which means that we have achieved like the approximation that we desire, and the error is close to zero. That's why you see a lot of white images here, right? Okay. So this is about LoRa and this is a small plot that I tried to show you guys here. If you have any questions, if you have any doubts, please mention it in the comments and I will try my best to answer them. This was the whole motivation around learning matrices, understanding determinants, right? In the next video, we will try and understand the Gauss elimination method, and we will try us and solve it using the Python samples that we have. If again, like if you have any doubts, any suggestions, please mention in the comments. I will try and address them as much as possible. Thank you, and please like and subscribe if you found this video useful. Thank you.